Now that we know where the definite integral came from, this integration of function f of x with respect to x from a to b, from the Riemann sum, f of x is the height of the rectangle times the base of the rectangle dx, which we made them so small, and then we add them all together with this integration sign. Let's take a look at some manipulations we can perform on this type of integral. If you swap the order of the start and the end points like this, so that a comes down here and b goes up there, then you get this minus sign at the front. When it comes to integrating a function from b to a, it means that we start at b, this point. Let's call it b. And then we take a really small step, dx, like this. Not just one, we take it infinitely many times, again and again and again and again, until we get to this point, right here, point A, the end point. From this, we can assume two things. First, A has to be greater than B. Second, the direction of the small step, dx, has to be in this way, to the right, towards positive infinity of x. But here all of a sudden, we switch the order of the start and the end points. This means that we are now starting at A instead, which, by the way, is greater than B according to this. And this also means that we have to take a step backward instead, like this. Take a step backward many times until we get back to B. The key is right here, step backward, which in this case is going to be equal to minus dx. So it's going to be minus dx over here for each step, and it's moving to the left hand side towards minus infinity of x. And this minus sign right here for the backward step is going to show up again right here at the front, down here. And that's why every time you switch the order of the start and the end point of a definite integral, you are going to get a minus sign. Here we integrate from a to a. So this is basically just one point, x equal to a. And since this is just one point, it means that we can take a step, even if it's really small. And therefore, dx in this case has to be equal to 0. And this is going to go to 0 too, which means that the final result has to be equal to 0. Now let's move on to the next one, number 3. In this one, we have an integration of a function f of x right here, multiplied with a constant k. This k right here is a constant. And at this point, we also know that integration only affects the terms that depend on the variable, which is x here. Therefore, this k right here, which is a constant, is not going to affect this operation, and we can take it outside like this. And that's why it can show up at the front over here. Well, this also includes the case when k is equal to minus 1 over here. This is k equal to minus 1, and this means that we can take this minus sign outside. Just take it outside like this, and that's why this minus sign can show up at the front over here. And if you relate this to the first property, you can use this minus sign to swap the order of the starting point and the end point a and b. So this is going to be equal to integration of the same function, f of x, with respect to x, and now a and b are swapped. B comes down here, and a goes up here. Now number 4, what do we have here? Here we have an integration of a sum or subtraction between two different functions, f of x and g of x. In this case, we can distribute the integration operation, this integration sign, to each function, to f of x and to g of x directly. This means that we can perform the integration on each function separately. So we can perform the integration on f of x alone over here, and then integration of g of x alone over here. And then we can perform the addition or subtraction in the end over here. Now, last one down here, additivity. Well, this one is actually quite interesting. Let's take a look here. We have two integrations of the same function, f of x. So the first one is right here, f of x, and another one back here, f of x. However, they are over two different intervals. The first one from a to b, but the second one is from b to c. At this point, I'm sure that you can notice that the second interval, this one back here, follows the first one instantly, with no gap between them. They are connected by this same point right here, the end point of the first interval, and b right here, the starting point of the second interval. In this case, these two integrals can be combined into one, like this. And the new integral can start from a and go straight up to c right away, skipping the point b altogether. Keep in mind that we are talking about the exact same function here. So it has to be f of x and also f of x here. So if you see f of x and g of x, different functions, don't combine them. What is interesting about this additivity is that we can look at this property in reverse. Well, how does that work? Let's take a look here. Let's assume that you have a definite integral, any definite integral. Let's assume that it's this one, starting from a and ends at c. And now we apply additivity in reverse. This means that we can split this one integral into multiple integrals. So we can split it, make a note right here, this one integral into multiple integrals, multiple parts, as long as the intervals of the splitted integrals can be combined to be exactly from a to c. As long as they all combine to be this, it's all good. Also, you can split this integral at any points you want, as long as they are in between a and c. So you can split this at b1, or at b2, or at b3, or at any point, as long as they are in between a and c. Okay, I think we are done here. Let's move on to the next slide. Up to this point, we already know that if we have a function f of x, and then we perform the integration on this function, well, along this arrow. So this one is integration. We are going to get the antiderivative of this function, and let's call it big F of x. Big F of x. And don't forget this constant plus c that has to show up every time you perform an integration without starting and end points. And we call this type of integration without starting and end points indefinite. So what you see right here is indefinite integration. So let's make a note right here. This is indefinite. Integration. From that, we also know if we differentiate the antiderivative, if we differentiate the big F, like what we do right here, diff big F, we are going to get the small f of x. So the relationship between these two is something we already know. If you diff the antiderivative of a function, you are going to get the function back. It's going to be equal to the function itself. However, in this slide, we are going to look into this relationship in a little bit more details. First of all, let's have this graph down here. Y-axis. But the horizontal one is a little bit different, t-axis. And now let's assume that we have this function curve of f of t, something like this. And then we want to find the area between this curve and the t-axis, starting from this point right here, a constant a. And then the region is going to end at this point, around here. Let's call this point x. Now let's make a note right here that a is a constant. It stays the same, not changing. However, x right here is a variable, which means that x can change. It can increase, it can also decrease. You can pick any value of x you want. So the region that we are talking about here is from a and all the way to x. Let's call this region R. And if I want to find the area of this region R, it's going to be equal to definite integral of this function f of t with respect to t from a to x, which is exactly the same as what we have up here in the box. And this term that we see in the red box up here, this one, can be represented or illustrated by this region down here. The area of R, same thing. So let's make a note up here. This is the area of region R. And now we want to differentiate this box with respect to x. What is the meaning of this? Let's write it down. It means change of the area of R as x slightly increases. In other words, rate of change of area of R with respect to x. Of course, this is differentiation with respect to x. That's why you see rate of change with respect to x right here. So we want to know what's going to happen to this region R down here when x slightly increases. Let's do that. So let's assume that we take a small step to increase x, like this. Really small step. And then we assume the length of this line to be dx, differential x. And then when you take this small step, the new boundary is going to be here. I know that it looks quite big here, but let's assume that it's really small. And then let's highlight this region right here. And this green region right here is the change of the total area of R when compared to the red region. We used to have this region before, but now it has been extended to include the green region. So you can make a note that this green region is the change of area of R when we take a small step of dx. And now we want to calculate this area. Equal to what? Let's find out. So we already have the base, which is equal to dx. We know that. And now what about the height? Let's use this. The height right here, which is the function value at x. And since this piece is so small, let's assume it to be just a rectangle. So the area of this piece is going to be the height of this rectangle, which is f of x, times the base, which is dx. And this term right here is the same as this change of the area of R, d of this integral, which is equal to f of x times dx. And then you can see that we have this division by dx right here. So it can cancel with this term right here. And that's why we are left with f of x in the end, which is equal to what we have on the right hand side. And what we just saw right now is the Fundamental Theorem of Calculus, Part 1. The main idea of this theorem is if you integrate a function and then you diff it, you are going to get your function back. However, an interesting thing about this theorem is about this constant a right here. This a and also this a. This a disappears from both the left-hand side and the right-hand side of this equation. As you can see here, the left-hand side, no a to be seen. Same thing on the right hand side, no a as well. And this is telling us that a doesn't really matter in this calculation. And it's because we are interested in the change of the area of R. With respect to x right here, this x is the endpoint. So what really matters here is the endpoint. A doesn't really make an impact here. Let's make a note right here that this a is irrelevant. When it comes to the fundamental theorem of calculus number 1, because all the actions happen at the end of the region, over here. So let's underline this word. Once again, irrelevant. You don't need to care about this constant. Now there is one more thing that disappears from this equation, both from the left-hand side and the right-hand side of this, and that is this variable t. This one right here disappears. So no t on the left-hand side and no t on the right-hand side either. When you have an integral like this, when the first variable, which is t right here, gets replaced by a new one, a new variable, by this x right here. The new variable is usually on the starting or the end point of the integral. When you have something like this, we call the first variable that gets replaced as dummy variable. So in this case, t is dummy variable. It means that t is going to get replaced by x and disappear anyway. So we call it dummy. Now let's apply this theorem to these examples down here. Let's start with this first one right here on the left-hand side. So we have an integral of these terms, 1 over 1 plus t squared. As you can see here, these terms are a function of t. In other words, this is f of t. And now we want to find the integral of this, and the integral starts at 0. Starting point right here, which is a constant. Let's make a note here. Constant. And the integral ends at x, the endpoint, which is a variable. Make a note once again, variable. And in the end, we want to differentiate this integral with respect to x, right here. As you can see, we have an integral of a function of t, starting from a constant and ends at a variable. And then we want to differentiate this with respect to the new variable x. As you can see here, this is exactly the same as the formula we have in the theorem, which means that the result has to be this, f of x, just like what we have here on the right-hand side. So this is going to be equal to f of x, the same function, except that the variable has to change to x instead of t. This means that this is going to be equal to same function, same transformation, which is 1 over 1 plus. Now, we used to have t squared right here, but now t gets replaced by x. So we have x squared right here instead, the new variable. And that is it, the answer for the first example. Now let's move on to the second example on the right-hand side. Here we have an integral of these terms, 3t times sine t, which we know that this is a function of t, f of t. And this integral starts at x, which is a variable. Make a note right here, this one is variable. And this integral ends at 5, which is a constant. And in the end, we are supposed to differentiate this with respect to x. Find derivative of y with respect to x, which means that we want to find this, d of this integral, 3t sine t dt from x to 5. Diff this with respect to x. Now let's take a look at the integral that we have here. First of all, we have this function f of t, which is good, just like what we have in the formula. And then we have this variable down here for the starting point, which is different from the formula. Same thing here, we have a constant at the endpoint, which is different. In the formula, the endpoint is the variable. And this means that we cannot use the formula in the theorem right away. We have to put some work into this. It seems to me that the order of the starting and the endpoint is the opposite here. What about we swap them? Move x to be up here, and then move 5 to be down here. But as you know, if we do this, we are going to get this minus sign at the front, which means that this is going to be equal to minus same integral 3t sine t dt, and now 5 is moved down here, and then x goes up here. Now it looks quite good because down here it became constant, and up here became variable, which is exactly the same as what we have in the formula. So this is going to be equal to d by dx of minus integral from 5 to x 3t sine t dt. So this one is ft. And once again we have a constant down here for this integral and a variable up here for the endpoint, same as the formula. And this minus sign can go to the front. So in the end we are going to get this minus f of x, which is equal to minus, now let's take a look at this function f, 3t sine t. So it's going to be the same except that t is now replaced by x. So we have 3x times sine x. And that is the answer for the second example. Now let's move on to this one down here. Let's take a look at what we have. So we have an integral of this term, cosine t, which we know by now that it's function of t, f of t. And the integral starts at a constant, which is good, same as the formula. Constant here. And it ends at x squared, which is sort of like a variable, but not quite. What you see right here, x squared, is actually a function of variable. So make a note, this is function of variable. It's not x alone. This is x times x. And because of this, we cannot use the formula in the theorem right away. In order to use the formula, this endpoint, this whole term, has to be just one variable. But right now it's not. However, we can get around this problem by using one technique, and that technique is called substitution. So this technique is back. Sub. We want to make this whole term just one variable, and let's call it u. This means that u is going to be equal to x squared. And this is the main substitution we have here. And now once again, in the end, we are supposed to differentiate this y with respect to x. Find derivative of this integral. And by chain rule, we know that dy by dx is going to be equal to dy by du, the new variable, times du by dx. And now we have to find these two. Let's start with this one, dy by du, which is d of y, and that is integral of cosine t dt. Starting point is 1, end point used to be x squared, but now we use the technique substitution, so it became u. And then we need to diff this with respect to u. So here we have cosine of t, which is a function of t, f of t. Starting point 1, which is a constant. End point, just one variable alone. This one is variable. And it's the same as this variable down here, u. So this is exactly the same as the formula we have in the theorem. So let's use that. This is going to be equal to f of u, because the new variable here is u, right here and right here. So it has to show up right here. So this one equal to f of u. What about this one, du by dx? Let's find that. So from this, u equal to x squared, we know that du by dx has to be equal to 2x. Just diff this, you get 2x. So for this one, it's going to be equal to 2x. So at this point, we have this to be equal to f of u. So f is the same function, which is cosine, but now the variable changes to u. So we have cosine of u times du by dx, which is equal to 2x. As you can see here, we want to find dy by dx, which means that our answer is supposed to have x in it, not u. So we cannot leave this u right here. U equal to x squared. So in the end, we have this 2x times cosine of x squared as our final answer for this example. The fundamental theorem of calculus number 2 is the extension of number 1, which we studied in the last slide. So let's bring that back here. We had big F of x prime, which is the derivative of antiderivative, equal to d by dx, differentiation of this integral from a constant a and ends at a variable x. Of this function f of t, t right here is a dummy variable with respect to t, dt. What we have right here is theorem number 1. And this number 2 is the extension of that. I can just give you this formula on the right, which is the formula to calculate the definite integral, which most of you already know. But then you wouldn't know why it works. So let's take a look at the proof down here, so that you know why the formula works as it does. Make a note right here, proof for theorem number 2. So I'm going to start with the relationship in theorem number 1. This one, big F of x prime derivative of antiderivative equal to d by dx of this integral from a to x, f of t, dt. The next thing I'm going to do here is to take out derivatives on both sides. So I'm going to take this out, and same with this, which means that I'm going to get this relationship instead. F of x equal to integration from a to x, f of t, dt. And since this a right here is just a constant, it's just a name, I can change its name to something else. So I'm going to change it to c. And now I have this relationship, f of x equal to integration from c to x, f of t, dt. And now I do this. First one, let x equal to a. And second one, let x equal to b. Let's see what happens. For the first one, when x is equal to a, then our expression becomes this. F of a equal to integration from c to a. Notice this. Now x becomes a. Alright, continue. Same f of t, dt. And now for the second one, it's going to be similar. It's going to be big F of b, integration from c to b. Once again, x becomes b. Same f of t, dt. Now let's take a look at this function, f of t dt. As you can see here, t is the only variable we have in this integral. We don't have x anymore, which means that we can name t something else. We can name t x. So I'm going to change the t right here to be x. Same thing with dt right here, change it to dx. It's just a name, so I can change it to something else. Same thing here, f of t becomes f of x, and dt becomes dx. So in the end, you have this integration from c to a of f of x dx for the first one. And the second one, integration from c to b, f of x dx. And now let's try to find this term. Antiderivative at b minus antiderivative at a. It's going to be equal to, so first one, big F of b, which is this one. So I'm going to use this term right here, back here. So let's bring it to this equation. Integration from c to b of f of x dx. That is big F of b. Now minus big F of a, which is going to be this term. Same thing here, this term right here. So this is equal to integration from c to a, f of x dx. And the next thing I'm going to do here is to use this minus sign to switch the order of the starting point and the end point of this integral. So these two will be swapped. And now I have this. The front integral doesn't change, so same thing. From c to b, f of x dx. And now the second integral, I use the minus sign, so this becomes plus. And the second integral becomes, the starting point and the end point are swapped, so I have a down here and c up here, f of x dx. Now let's take a look here. We have two integrals of the exact same function, f of x, over two different intervals. The first one starts at a and ends at c. The second one continues right away, starts at c and ends at b. As you can see here, these two, c and c, are the exact same points, which means that we can use additivity property to combine these two integrals into one. So this will be equal to just one integral of the same function f of x with respect to x. And it starts at a, the first starting point, a right here, and it goes straight up to b, the last endpoint, b right here, skipping c altogether. What you just saw right here just now is the proof of the Fundamental Theorem of Calculus number 2, and it shows why this definite integral of fx with respect to x from a to b is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Same formula that we have here. Once again, this is the extension of the first Fundamental Theorem of Calculus number 1. Extension right here. Now that you have seen the proof, from now on you know why this formula works and why it's okay for us to use it. Also, let's make a note right here that this formula is for calculating the definite integrals. So this one for definite integrals. Now let's apply this new formula to these examples down here. Let's start with this one. So we have an integral of these terms, which we know it's a function of x, f of x. And this integral starts at 1, which is a constant, and ends at 4, which is also a constant. Since the starting and the end points are constants, you know right away that this is a definite integral. So make a note right here that this one is definite integral. So we can use our new formula here. But first of all, I'm going to express this function f of x to be in a form that is easier to work with. So let's do it right here. F of x equal to 3 over 2. So we have square root of x, but I'm going to use this instead. X to the power of 1 over 2 minus 4 divided by x squared, and I use this instead, x to the power of minus 2. When I have polynomial terms with simple powers like this, it's easier to work on. It's easier to apply the power rule. So our integral becomes this, equal to integration of 3 over 2 x to the power of 1 over 2 minus 4x to the power of minus 2 with respect to dx from 1 to 4, just the same. And now back to the formula. We know that we have to find the antiderivative of this function. We need to find the big F. So we need to find the antiderivatives of these terms. So it's going to be equal to, let's start with this one, the first term, 3 over 2 times x to the power of 1 over 2. 3 over 2 is a constant, so I leave it alone. And now I find antiderivative of x to the power of 1 over 2. Integrate this, I know that it has to be the same polynomial term, x to the power of something. But now power has to increase by 1, so it becomes 3 over 2. And now I have to divide that number down here, 3 over 2. Just like before, if you increase the power by integration, you have to get rid of that number by division right here. Let's move on. Let's find the antiderivative of the next term, this one. So I have minus 4 right here. The constant doesn't change. And then I need to find antiderivative of this x to the power of minus 2, this one. And just like before, it stays a polynomial term, x to the power of something. And now the power increases by 1, from minus 2 to minus 1. And once again, I need to get rid of this number by this division down here. Division by minus 1. Same term. Minus 1 over here and minus 1 down here. Now let's simplify these terms before we continue. This 3 over 2 cancels with this 1 down here. And this minus 1 cancels with this minus sign over here. So it becomes plus up here. So what we have right here is the antiderivative of the whole function, big F right here. And from the formula, we have to evaluate this antiderivative at two values, at b and a. So let's write everything over here again, equal to x to the power of 3 over 2 plus 4 times x to the power of minus 1, and that is equal to 4 divided by x. It looks nicer this way. And now we evaluate this at two values, a and b. And this is equal to, now b goes in. This b goes in here and goes here. And that is equal to, first one, 4 to the power of 3 over 2 plus 4 divided by 4. This is big F antiderivative at b. Now minus, and it corresponds to this minus sign right here. Big F at a, the next one, we need to find big F of a. And it's equal to, now a goes in, right here and right here. So this becomes 1 to the power of 3 over 2 plus 4 divided by 1. And this is big F at a. This term right here, 4 to the power of 3 over 2, this is equal to 8. And this one is equal to 1, 4 divided by 4. This one, of course, this is equal to 1, and this is equal to 4. So in the end, we have 8 plus 1, which is equal to 9, minus 1 plus 4 equal to 5. So we have 4 as the final answer for the first example. Now let's try this one on the right. Once again, we have an integration of these terms. And we know this is a function of x, only x variable in here. And it starts from minus 2, a constant, to 2, also a constant. So we know right away that this is a definite integral. Definite right here, equal to. And now we have to find antiderivatives of these terms, all of them. So let's start with this one, x cubed. The antiderivative of x cubed, of course, is the same polynomial term, x to the power of something. And now the power increases by 1 from 3 to 4. And I need this division down here, divided by 4. Once again, same term, 4 and 4. And now next one, minus 2x. So minus 2 stays the same, the constant. And now antiderivative of x. So x the same, the power increases by 1 from 1 to 2. And once again, division down here, divided by 2. And now last term, antiderivative of plus 3. So we have plus 3x. And now we evaluate this antiderivative of the whole function at two values. The starting point minus 2 and the end point 2. And this is going to be equal to, and now this 2, the end point goes in, right here, and right here. So we have 2 to the power of 4 divided by 4 minus 2 times 2 squared divided by 2 plus 3 times 2. And this is the antiderivative evaluated at the end point, which is 2. So this one, big F at 2. Minus, and now the second derivative evaluated at the starting point. So this minus 2 goes in here, and right here, also right here. So we have minus 2 to the power of 4 divided by 4 minus 2 times minus 2 squared divided by 2 plus 3 times minus 2. And this is big F evaluated at minus 2, the starting point. And this first term right here is equal to 16 divided by 4 equal to 4. Minus, so this 2 cancels with this one. So we have minus 4 right here. Plus 6. And back here, we have also 16 divided by 4. So this is 4. Minus, this 2 cancels with this one. So minus 2 squared, we have 4 right here. Plus, back here we have 3 times minus 2, we have minus 6. So this 4 cancels with this one. This 4 cancels with this one. So in the end, we have 6 minus 6 right here. So we have 12 in the end. So this is equal to 12, which is the answer for this example, number 2. Now let's move on to the last one, this one right here. So we have an integration of 1 over 2 times cosine x plus absolute cosine x. This one is a little bit different because of the absolute. But first of all, I'm going to move the constant 1 over 2, this one right here, to outside the integral, like this. And then I distribute the integration to each subfunction directly. So first one right here, 2 cosine of x, and then 2 absolute cosine of x. And now we have two integrals equal to, first one, 1 over 2, first integral of cosine of x dx from 0 to pi, just the same, plus the second integral, 1 over 2, integral of absolute cosine of x dx from 0 to pi again. And it's going to be equal to 1 over 2. Now we find the antiderivative of this cosine of x. What do we need to diff in order to get cosine of x? Of course, we need to diff sine of x. So we have sine of x down here. And then we need to evaluate this at two values, starting point 0 and end point pi. I'm going to leave the second integral for now and work on the first one. So this is going to be equal to 1 over 2 stays the same. And now pi goes in, the end point right here. So we have sine of pi. Minus, now 0 goes in, the starting point right here. And we have sine of 0. We know that sine pi is equal to 0, and sine 0 is equal to 0 as well. This means that everything here goes to 0. Now let's take a look at the second integral. We need to integrate absolute cosine of x. The problem now is the absolute value, which we haven't worked on yet. When you see an absolute value of a function like this, the first thing you need to do is to plot the graph. So graph right here, y-axis and x-axis. So y right here and x right here. First, we plot the graph of cosine of x, and it's gonna look like this. Right here is pi over 2, and over here is pi. And this is the graph of cosine of x. What about absolute cosine of x? It means that everything has to stay positive, which means that the second half of this curve has to be flipped up. It should look something like this, flipped up version of the curve down there. And the first half looks exactly the same because it's already positive. So this one right here is the absolute cosine of x. Everything is positive. And now we want to find the definite integral of this absolute cosine of x from 0, the origin, to here, pi, which is going to be the area under the curve, this area, plus this area. Another thing that we know here is that the area of the first half, this one, has to be equal to the area of the second half, this one. Which means that this integral right here can be found by the area of the first half times 2. So this is going to be equal to the area of the first half from 0 to pi over 2 of just cosine of x dx. As you can see here, the first half, the curve of absolute cosine of x and cosine of x is the same, so we can use cosine of x in our integral. And then we multiply 2 right here, so that we include the area of the first half and the second half with this 2. So this is going to be equal to 1 over 2 stays the same. And now we have the new terms, times 2 integration of cosine of x dx from 0 to pi over 2. And we can see that this 2 can cancel with this one right here. That's good. So plus down here. And now we have to find the antiderivative of cosine of x once again, right here. What do we need to diff in order to get cosine of x? Of course, we need to diff sine of x. So sine of x right here. And now we have to evaluate this at two values, the starting point and the end point, which is 0 right here, 2 pi over 2. Now let's work on this one. So first of all, pi over 2 goes into here. So we have sine of pi over 2 right here. Minus, now the second term, 0 goes in right here. So we have sine of 0 back here. And this one, sine of pi over 2 equal to 1. Sine of 0, 0. So this box right here, the second integral, is equal to 1. And we already know that the first integral is equal to 0. And now the answer for this example is equal to just 1. There you go.